there it is. Give it a second to pop up. All right. Hey, guys. I'm Jason, PhD student in robotics here at Georgia Tech. We're going to be talking about some pretty straightforward things, kind of more quality of life stuff with ROS. So nothing too intense today. I'll show you guys some demos and kind of how I use it in my own research because that was convenient. So we'll do that. So starting off, so you guys have been mostly using, some of the exercises have used roslaunch, but most of them you've been using rosrun. So rosrun's really nice. You get to run your node. You can run it from anywhere. But you kind of have quickly run into this problem of the fact that you have like a lot of nodes, and you guys are doing simple programs. Like when I run my research, I probably have 30 to 40 nodes running at any given point. And you're like, that's a lot of nodes. It is a lot of nodes. So I don't want to have to open up 40 terminals to run 40 different commands. So this is the convenient thing of roslaunch. Like I could launch this whole thing. This is RQT plot of some arbitrary thing online. I can run all of this with one roslaunch file. So I can essentially run this node. You guys can see my cursor, right? Yeah. So I can run this node, this node, this node, the whole thing, all with one command, and they all start up well. And it's really convenient because I can control all of them from one terminal, so I don't have to have 40, 50, whatever number of terminals you have. So here's kind of the key thing. So roslaunch file is an XML file. If you're not familiar with XML, it's essentially this thing you see right here. So you see these tags on either end. And then kind of what's centered around it is whenever you want to run a new node, you're going to have this node tag right here. So kind of the key components. You have the name of your nodes. This is essentially what's going to show up when you do ROS node list. And you can do ROS node info on it, all of those things. So this name is only used in those kind of contexts. It's not actually used in your program for any given point. So you have the package. So we talked about packages before. This is essentially where your file is located. What package it's located in, so that when you do that roslaunch command or that rosrun command, it knows where to search for the actual executable. Type is the name of the executable. So this is what you set up in CMake. So if you guys have seen like our add executable file and we put the name there, you want to make sure this name matches to that name. And did I do package twice? Nice. So we also have output. So output screen. This is really convenient. When you guys do rosrun, it automatically takes the standard out. So that'll be rosinfo, cout, all of those different kind of output commands, and prints it out to the terminal. With roslaunch, since you're usually launching a bunch of them, you usually want to send it to a kind of a log file. So automatically they sent to log files, and if you want it to actually print out to the terminal, you need to do output equals screen. Otherwise, it'll just silently print to the terminal, and you'll have no idea why you're not getting any output for your node. So that's a really important one to keep in mind. If you ever don't get output that you're expecting to get, make sure output is equal to screen. So this is what it looks like if you were to run a node, roslaunch something. So I do the command at the top, roslaunch, what the package is, so week 4 exercises, and then what the actual launch file name is, exercise 4.1.launch. It'll print up a bunch of things. The cool thing about this is it'll actually start up a ROS master instance, which you can see here, process master. If you don't have one running, the key thing to keep in mind here is if you're using a couple launch files or you launch this node afterwards, if you kill this terminal, you will kill your ROS core and you'll have the same issues that you had before. So make sure to keep that in mind. So this is just another terminal of launching it. Essentially the same things, a bunch of parameters get printed out. We'll go into that more in a second. So what I would talk about is, we have these launch files. They're really cool. We can launch a bunch of nodes. But what if we have parameters? And we want to, essentially what you want to do a lot is you write nodes, but you don't really have the exact tuning of what those nodes should be. So let's say we're running PID. So I want to write one PID node that I can then change my P, I, and D as needed while I'm tuning without having to recompile my entire code. And that is the whole point of ROS param. So there's this ROS parameter server that's running in the background, which is tied to ROS core. And if you kill your ROS core, you'll kill your ROS parameter server. Demos and walk you guys through a little bit more of this in detail. So I'm just kind of giving you the high level, and then we'll look through it in a little bit more detail. So here are the kind of the key commands. You can look at all of this stuff on the command line. So you have ROS param list, which shows you all the current parameters that exist. The exact same namespacing rules apply that you have with nodes, so you can namespace your parameters. So we also have set, So you can essentially change a parameter value. You can get it, so you can print it out to the screen. You can load a YAML file. We'll get to YAML files in a second, but essentially instead of doing a bunch of these really small kind of verbose commands, you can just make a really simple file that is easier to load. We can also dump all of the parameters into a file so we can read them back later. We can also delete them from the parameter server. So again, really important, your parameter is tied to the lifetime of ROScore. So if I start up a ROScore instance, I set a bunch of parameters, I run a bunch of nodes, and I leave ROScore running for the next week, those parameters will continue to be there unless I explicitly delete them. But if I'm constantly starting up and killing ROScore, those parameters are not going to stick around. They're only going to stick around as long as the instance of ROScore in which I launched them is there. So it's really nice about these parameters, so we can set them, we can change them. There's a little bit more advanced thing which is called dynamic reconfigure, where you can change them while the node is running, which is really convenient for tuning. So what you'll see here is, so we have some basic C++ code. So we're creating a ROS node handle. So we create a standard node handle, and this thing we usually tend to call a private node handle. So this is in the namespace of the node. So the node we have here is a RUCO detector. So essentially that means what the parameters will show up is a RUCO detector / whatever the parameter name is. So if I had a PID node named PID, I would see PID and then /P would be my P, /I would be my I, /D would be my D. So this essentially allows you to, without having to type out the full namespace of the node, grab the parameter at that namespace level. So that's what the tilde in the constructor means. Essentially it means that all of the relative paths will be indexed from the node rather than the global namespace. So here, this is kind of how you would get a normal parameter. So we create a string called image topic. So what we're going to do is call this private node handle because you want to get it in the namespace of the node. We get .param, and then we're passing in the template argument, which is we want to get a string out. It's really convenient for setting topic names. So that's one of the main uses of ROS parameters. So what you also have here, so I take the name of the parameter, which is image topic. So I'd be looking for a RUCO detector / image topic in the actual ROS param list. Then I'm going to grab essentially what variable I want it to be set to, and then I can also specify a default value. There's another way to call this, which is get param, where you set no default value, and it will essentially exit if it doesn't find a parameter. And that one is just kind of up to what kind of node it is. Does it make sense for you to have a default parameter that's defaulted to? In this case, this is the default parameter for the topic name that I use. So now we can take that image topic that we set based on the parameter. We can use it to subscribe to a topic, and then we subscribe to that topic. And essentially, that means I can change what topic I'm subscribed to by just changing the parameter before I launch the node. So since I don't have dynamic reconfigure set up, and there's not a way to do that with subscribe, this does not change the instance of a node. So if I start up this node and I change the parameter, the node is still subscribed to whatever value it was when it was launched. Because as soon as this program runs, it grabs that topic, and you can see there's no way to change it afterwards. Okay. So we can also set these parameters in launch files. So you'll see this pretty frequently. We're moving a little bit more to the YAML files, but down at the bottom here, you have parameter name. So this is the image topic, and what is the value? So you can see that this param tag is inside the node tag. See how there's no closing slash here like you had previously. So now you can see the launch tag goes from here to here. The node tag goes from here to here. And you have the parameter tag, which is closed on the same line. So we essentially just create an image topic, and this is defaulted in the namespace of actually a RUCO detector node. So we look for that parameter. Whenever in the actual code, we'll look for it there. And that'll be the actual global namespace of what we're looking for. And then the value is just whatever the value is. So, but in YAML, so this is another grab from my research, constant theme here. So a lot of times what you'll use is if I'm doing like a single parameter, I'll usually just put it in the launch file because it's easy and it's like a single line. But if I start having, like, this is for an actual state estimator configuration, like, you can see that this is about a quarter of the parameters that I'm having to set. So there's a bunch of different parameters that I want to set, and it's easier just to have it all in one file rather than 100 of those param tags with all of the namespacing that's required. So how these files are set up is essentially this would be the node namespace. So then if I load this file, what you'd see is that the global namespace, if I did ros_param list, you'll see factor_graph estimator /debug, and the value would be true. Or factor_graph estimator /isam parameters /relinearization threshold would be 0.01. So that's kind of how to parse these files. And CLine does a pretty convenient wrapping of those, so it'll help you keep track of that. If you have more than like 5 or 6 parameters, I'd recommend doing YAML file. It's just a lot easier. So what does it look like when I actually go to load this config file? So instead of writing out all these different like topic names and all these things as you see at the bottom here, what I would just have is I'm going to do a load a single config file. This is actually just giving you the location of the config file, and then I load it somewhere else. But there is a way to load this directly into the ROS from a launch file. So a lot of times what you'll see is a config file at the top level of the actual note of the package, and you'll see config folder and then the actual .yaml file. That's what you can see here. So in this launch file, a lot of times this autorally estimation package or whatever your package is will be in an arbitrary CACAN workspace, and you can have multiple, and they can be in different places, and they can be hidden inside projects in different locations. So you essentially can use this find package command, which will essentially, this $sign all the way to the closing brace or closing parentheses will be replaced with the absolute path of where that is in your system at runtime. So essentially, as I launch this node, it does this find package, finds the package, replaces the full path, and then this will work on everyone's system without me having to hard code the full path. And that's really convenient. All right, any questions on parameters or roslaunch? We'll look a little bit more in depth in a second. Okay, taking that as no questions. So we're going to talk a little quickly about Gazebo. So Gazebo is a simulator that comes essentially out of the box support with ROS. It's built by the same company, I would say would be the right word. So with Gazebo, you can create these arbitrarily complex simulation environments for your robot to drive around in. And it's really nice because they have a nice convenient interaction with ROS. And essentially what you'd want to see as you set up your simulation environment is everything that your actual robot publishes. So all of the nodes that directly interface with the hardware should be mocked in the simulation environment. So for the car on the top left, which is my research auto rally, I can run the exact same code on the simulation that I can run on the hardware because the topic names are the same. What data is coming through is exactly the same. Everything is exactly the same. So I know if I have my code working in the simulator, it should at least run on the actual hardware, if not work. There's obviously a big gap between simulation and the real world. Physics are also super janky, and you'll see that in a second. And then you can change the actual noise readings on the sensors, and they're a lot cleaner than they are in the real world. But at the same time, it gives you a really easy way to test your code without having to take a hardware platform out every single time. So there's two kind of main files in Gazebo. Unless you guys actually start creating files, you should never really have to worry about this. But at a high level, what you have is a world file, and that describes the world. So on this back screen, essentially my world file would define everything except for this car. So the car would be gone. I'm essentially saying like, oh, there's a cone here, there's a cone here, there's a tree here, there's a shed back here, there's this weird bush thing here, there's like some construction barrels around, all these different things. You can see down here in this larger track, we have a bunch of Aruka markers, which are essentially easy to detect with computer vision and used for localization. So that's within the world file. And the URDF file essentially defines the robot. So if you ever use the package transform, TF2, this is where it's actually pulling all that information from and doing the transforms. So we talked a little bit about local coordinate systems. But essentially what the URDF file specifies is, so I have essentially the center of my robot is somewhere. What is the transform from that to the wheel? or transform from that to the IMU, or essentially what is the XYZ roll pitch yaw offset between all these different points, so that if I do get a sensor reading from my LiDAR, I can properly transform it into the coordinate frame of my robot without really having to worry about it. And this is kind of the beauty of TF. And we'll look at a thing in a little bit called RViz, which uses TF pretty extensively for visualizations and just makes understanding what's going on a lot easier. So a big point to point out is a lot of times you guys will not be able to run simulation as fast as the real hardware, or things will be different. It'll just make more sense to slow it down. Maybe you want to debug your code at a slower speed. So there's this thing called sim time. So essentially what that means is that you can have time increasing that does not exactly match the wall clock time. And you can actually play around with things like Gazebo. You can actually pause time, and you can step through topic by topic as the car drives around. And there's one parameter that's essentially controlling whether or not it's using sim time or real time. Essentially the difference between a fake clock and a real clock is this use sim time parameter. So a lot of times you'll see in a Gazebo environment that it'll set the main launch file will set use sim time to true. And if you ever see that and you don't restart your ROS core between running sim and running the actual hardware, since that use sim time parameter is still around, it will try to use sim time, and then obviously you'll have an issue because no one's publishing a clock, because you're expecting, the hardware is expecting that it's using the system clock, and the system clock is essentially not running with respect to Gazebo. So if you're ever confused why topics don't seem to be moving, make sure sim time is correct. I'll show you guys what our simulation environment looks like. My research. So this is our Gazebo environment. You can move around with, essentially I'm on select right now. So if I left click and I shift around like this, if I right click, I can zoom in. So I can take these models and I can move them around and do what I need to. I can take them and I can rotate them, which is really convenient for when they're in the wrong location or you just want to play around with it. And I can also scale them. I don't think this will work, but yeah. Some models are not as easy to scale as others. So right now I do have it paused. So I actually have the code running already. So if I unpause it, what you'll see is the car starts driving around the track. The frame rate might be pretty bad. So you guys can see down at the bottom, of course my screen does. There is a real sim time parameter at the bottom right here, which is sitting at 0.8, 0.86, 0.87. So I'm only running not exactly real time, but I'm running pretty close to real time. And this is kind of what you'll typically see in Gazebo as you drive around. It'll depend a lot. If you're in a VM, it'll be a lot slower. I highly recommend, if you do have a slower VM, under physics, there is a way to essentially change how many steps it's using for the actual simulation environment and essentially what the target real-time factor is. And just try slowing that down because it'll help you debug your code. And it's also really convenient. I use it a lot to kind of look at stuff in a little bit in slower motion. You can also pause stuff and you can step through individual topics. So it'll publish a single topic. You guys probably can't see that it's actually changing because it's so far away, but I promise that it is. So if we zoom in a little bit more, we can kind of see what I'm talking about with this URDF file. So if we look at over here on these links, so this is alpha, it's called alpha. We have all these different links that correspond to different parts of the car. So let me grab. So that's a wheel. So essentially somewhere in the URDF file, I've said that there's a transform from the base link to the wheel. The wheel is right there. Cool. All right, so that's high level Gazebo. Does anyone have any questions about that as I switch? I will take that as a no. So now we're talking about RViz. So RViz is really nice. So you guys have used RQT Image Viewer. You've used RQT Plot. You kind of found that ROS topics visually that's much more appealing and kind of useful for debugging. But there's a much bigger step to that, which is RViz. So a lot of times what you're kind of seeing is the robot like when you echo an individual topic, you really don't get a sense for the 3D space and kind of what you're looking at. And this is what ArtViz can really give you. There's a lot of great visualizations that come already packaged in with standard message types. So if you publish those standard message types, you just get those visualizations out of the box. And you can do some pretty useful things to explain what's going on with your code and also debug it at the same time. So there's a couple of really important settings in ArtViz. So as we talked about, you have the URDF file, which defines your robot and the reference frame of everything in your robot. That is automatically connected with usually a thing called ODOM, which is the global reference frame. So at the very top of ArtViz, and I'll show you guys in a second, there's this thing called the fixed frame. And if ever you're getting an error that says cannot find transform, or like it's not published properly showing whatever you want to show, usually it's because you don't have the correct global reference frame, and ArtViz doesn't know where to plot it with respect to the one that you do currently have up. So keep that in mind, and this is why the frame ID part of the header message is so important, because it is exactly telling ArtViz and telling everyone else that I got this sensor reading from this sensor, and that essentially looking in the URDF file, I can figure out where that is in relation to everything else. So a lot of times you call these TF trees, so you can kind of see here on the left, right. So we have ODOM, which is our global reference frame, which is then connected to this, I think it says base plate, which is then connected to the actual robot itself. So a lot of times you'll kind of see these floating links around. I don't have a good visualization of that for AutoRally, but this is pretty standard. Usually you want a base that is, usually you have a thing called base footprint, which is the center mass of your robot, but at the ground level, or essentially ignores Z, and then you'll have the base link, which is kind of the center of your mass. It's though you can kind of put it wherever you want. You just need to find a reference frame for your robot. Okay, so what we're going to look at is, this is actually a picture from ArtViz, obviously with a couple of tweaks here. So this is from my research. We do some sampling-based controls, and all you need to understand from this picture is that essentially my robot is in a position, and then I have a fake robot in another position, and I do essentially that sampling-based to figure out where I should be driving and where I shouldn't be driving, and then I do an average of those, weighted average, and I get these trajectories. So a very complicated thing to look at. Like if I was looking at this visually, looking at it just, I'm probably publishing, I don't know, a couple thousand or so paths right now. I would not be able to contextualize what is currently happening, but you guys can very cleanly see that essentially here are the real samples, over here is the real system, and it's tracking back to the nominal system. And that is all you need to understand from this picture. And you can also see the track boundaries here. And I'll just do it really quick. So there's also this really cool utility called Rosbag. You can create these things called bag files, and essentially what that allows me to do is to record the ROS system as I drive around or as I do my robot thing, and then I can play back the topics in essentially the same order that they were recorded in. There's a little bit of weirdness, but you'll probably never run into it or never run into it being a big problem. We're going to test this more next week, but essentially when you hear, you'll see in week, the computer vision exercises on Saturday, you will see that you will be getting a bag file. It'll have a bunch of images in it. All you need to do is run the launch file, and it'll automatically play the bag file. But essentially all you're doing is you're taking robot that was recorded, data that was recorded on a robot when it was actually driving around, and just publishing it back as though it was new. And it allows you to debug your code really conveniently. So this is the AutoRally ArtViz config that I typically use. Let me actually unpause the simulation environment. So as you can see here, it's updating. You guys are probably a little bit slow, but it's essentially updating in real time from what I've seen. And I will pause and zoom in. So I have it on a specific view. So essentially the right swivels it, and then if I hold shift and left click, it moves around, and then right is to zoom. So I have essentially these arrows that represent where my robot is and what direction it's facing, and then I have these messages that are essentially saying where are my samples ending up in the actual 3D space. and then I have my track boundaries also published. So you can also see on the my screen die. Yup. Try to watch that better. So you can also see here on the left that I actually have a live view of the camera feed. So what's really nice is I think 2 teams will have this set up, probably 3 teams actually. I can actually view these topics on a different computer. So everything for my research is running on the actual robot itself as it drives around, but I can essentially view the same information that we're currently looking at from a laptop 100 yards away. So I can see what's happening with the robot in real time, which is really, really cool. I will just run that around for a second. So there's a couple things to point out. Remember how I was running at a different sim time? And I've also been pausing and starting time. So you can see here that the wall time elapsed at the very bottom is close to 3,200-ish. So
Jason, I think you stopped sharing your screen.
Stop stopping. It just killed. I don't know why, guys. So let's keep that up there so I can see it. So the wall time elapsed, so essentially how long it is in the actual seconds with the wall clock. You can see that the ROS time elapsed is significantly smaller, and then it's really hard to tell right now, but you can actually see that these two are not incrementing at the same rate. So that's what it looks like driving around simulation. I'm going to kill it, and I'll show you guys what it looks like from a bag file. And then we should be good. So here is what you would see if the robot's actually driving around. I'm not doing all the fancy publishing because unfortunately that was after this data was recorded. So over here is kind of the views that shows you all the different topics. So you can change what topic that you're looking at. So let's give it to the actual, it's going to complain. Oh. It is not showing the images. That's nice. Oh, it's on right camera. So you have to correctly select the right topic. Sorry. There we go. Nope. Okay. Well, I'll stop playing around with it. But essentially, you can view the images and you can see live data. So this is actually of the robot driving around in the physical world. It looks a lot better when I actually have the image working, but I'm not going to sit around and play with it. So that's RViz, Rosbag, Gazebo parameters, kind of at a high level. If you guys have any questions, we can go through a little bit more detail on parameters. But thank you. Hopefully that was helpful. That's all I got.
All right. So if that's all, I guess we can stop the recording.